starting time. It's really nice to see so many people here. Rich Davidson, who usually runs this class, got stuck in Atlanta on a business trip, so he asked me to fill in for him on the first class. So I don't know how he usually does this, but I probably will tell you some of the same stuff that he was going to tell you. But let me figure out who all is here. How many of you are ham radio operators already? And are you here for upgrade? To learn about upgrade?
Yeah.
From what to what?
Code general to advance.
Oh, good.
Or extra, excuse me.
General to extra.
Right.
See?
Okay, well, you may hear some things that you already know then for today, because it's the first class. But hopefully I'll throw in a few things that can help you understand what it takes to become an extra. For those of you who aren't hams already, are you here because you've always been interested in the hobby, or you know someone who does the hobby? Want to do it with them, or what? I'm often told, I've been a ham radio operator since 1970, and it was very different back then. But people often ask me, what good is ham radio anymore? Because you can just get on internet and talk to someone all over the world. That used to be what we did. We did many things, but the one thing that hams could do that most other people couldn't is talk to people in other countries far away. And my answer to them is that, first of all, ham radio isn't for everybody. Though some would like to think it is. But it's for the people who don't just want to talk to someone across the world, but also want to understand how it's done. When you get on internet, there's someone else, many other companies that are providing the communications for you, and you're just on one end and someone else is on the other end. When you're doing it with a ham radio, you control every step of the way. You create a signal, you put it into an antenna, the antenna goes out into the atmosphere, and I think one of the later classes will talk about how a signal can travel that far around the world, actually completely around the world. And then on the other end, there's a person who did the same thing you did. They put up an antenna, pulls in the signal, and they hear you. And that, at least is, for me, that's the most important part of doing the ham radio, that you understand how the signal's getting there. You don't rely on anything in between. You don't rely on anybody in between. If everything else fails, ham radio will always be able to communicate because the ham radio operators know how. But today we're going to start with the very basics. Why do we learn about electricity? Obviously, because everything that makes a signal uses electricity. But if you think about it, there's a continuum from a battery, from DC, all the way up past electricity, past radio waves, to light and beyond. It's all the same stuff. The light that we see, that our eyes pick up, is the exact same energy that our radios send out, except at a different frequency. That's the same energy that comes out of a nuclear reactor. The gamma rays that come out of a nuclear reactor are just a different frequency. The ultraviolet, different frequency. A microwave oven, different frequency, but it's all the same stuff, electromagnetic waves. And it's important to realize, and actually it's funny because in today's world, part of what I do is I sit on a committee at the FCC, and we tell the FCC about what's coming down the road for new communications. In today's world, the FCC doesn't allow anyone to go above a certain frequency, up to 600 gigahertz. But we're proposing that they allow it, to let people start communicating on those very high frequencies. In comparison to, I recently read a book on the development of radar in World War II. And what we think of as radar is very high frequency stuff. Today it'll tell us what the weather is. It's indispensable for, as we know, for airline traffic after this last disaster. And yet, back in as early as, or late, not so long ago as World War II, it didn't exist. But the funny thing is that back then, they thought that a really high frequency was 400 megahertz. We use 400 megahertz all the time. Our cell phones are at 800 megahertz and higher. But back then, you know, as technology advances, we're able to work with faster and faster signals, the faster, higher and higher frequencies. Back then, some of the radar that they used in World War II to detect German planes was around 200 megahertz, very low frequencies in comparison. But that's what they could work with the technology of the day. It's all the same though. It's all got an electrical component and magnetic component to make an electromagnetic wave. Let me start at the bottom of the frequency spectrum, and that is with DC direct current. So we know what DC is when we buy a battery. You've got batteries generate DC, or actually store DC and give it back to you. DC stands for direct current. That means that you have a positive and a negative, and the current flows from positive to negative directly. It's direct current. There's no variation. It's always the same. Now, arrow there to show you the direction. If we go down to the molecular level, because everything is made like metals, things, all the molecules have electrons in them. Electricity, electrons. Electrons is part of an atom and has a negative charge. And as we know from magnets, like charges repel and opposite charges attract. So what seems a little strange there is if you have an electron, what direction will it be flowing? Anyone have an idea?
It'll be attracted to positive.
Yes, so it's going to go the opposite of my arrows. So the first thing to confuse you with is that electrons flow from negative to positive, but in electricity, it's just a concept that current, electrical current, flows from positive to negative. It's all the same stuff though. There's nothing called current. There's just a flow of electrons. And because of historical things, it was decided that current would flow from positive to negative, the opposite of the electrons. But really what happens is when the electron flows this way, it leaves a gap for another electron to go into. So if you follow the gaps, they're flowing this way. Let me try and show that pictorially. If you have an atom with an electron in it, and another atom without an electron that wants the electron's going to jump from this atom to that atom. And that leaves you now, and sometimes we call them holes. There's a hole where that electron was. So the electron went this way. Here, let's draw the hole. But the hole went that way. So the holes are what we're calling current. And holes are just a concept, they don't really exist. The electrons really exist, they're little particles. And they move in this direction. It all has to do with a minus sign. If you do it wrong, your sign is wrong. Instead of positive is negative. But what's important for us to realize is that if we have a battery and we hook it up to something, there's going to be a flow from positive to negative. And that's all we're going to be concerned with. The other is just interesting, but it's not going to affect the way you understand this. Now, one thing about electrical circuits, what's the second word there? Electrical
Circuit.
What does it mean?
You have to have a workload, you gotta have a
Connection.
resistance.
Yeah, but what is circuit? Why the word circuit?
Well, it's a complete loop. You gotta
Okay,
have a-
that's the key. Electricity always comes back to where it started. In other words, it's a physics principle. Matter, this is matter. You know, an electron is part of matter. It's neither created nor destroyed. There are no more electrons at the end of the day than there were at the beginning of the day, and no less. There's the same number, always. They've just moved around, okay? For a circuit to do its work, it goes it comes back to where it started. So if this is your battery, the electrons, or let's just say the holes, the current, flows out of the plus, does work, and then comes back to the same battery. If it doesn't, what will happen?
It's an open circuit,
Okay, and then what happens?
nothing.
Nothing, it doesn't flow. If you were able to pull those electrons out of the battery would collapse on itself and disappear. Can't happen. So there's always a circuit. Everything electrical is a circuit. Lightning, lightning affects us a lot. It's also a flow of electrons and electricity. Does lightning have a circuit? Yes, no?
Yes,
Okay, and what is the circuit?
from positive to negative.
Okay, but I mean, what,
Through there,
from where to where?
cloud to ground, or cloud to cloud, or cloud
Ground
to
is,
you, or,
ground is the key term here. Ground, and we talk about ground a lot, in all electric, and everything electric, but also, you know, in ham radio especially, we use ground a lot. Everything wants to go to the lower, to the negative, the lower potential. Ground is the lowest that we have on Earth. So lightning, which is generated by matter up in the air, it pushes around and pushes its electrons around, just like wind will do that. Static electricity you're familiar with. That's just electrons being pushed on or off of something, and then they try and get back. So that's what happens with lightning. You build up charges in the air that try and get back to the ground, because it's a lower potential. So those are the basics of the movement of electricity now. Next step. How does it go from one place to another? Well, let's think now, a good way to compare is, let's compare it to water. All right? If you have water in a reservoir, and a pipe coming out of that reservoir, will the water flow through the pipe? Usually. The answer is yes. You could have all said that. But Why does it flow through the pipe? Because the water's under pressure in the reservoir.
Gravity.
Gravity creates the pressure and pushes it through the pipe to a point of lower pressure. So pressure always tries to equalize. In electricity, we have something called voltage. So the voltage, and voltage is really considered, it's not an absolute, but we'll consider it as a differential. The difference between the pressure at one point and another is the voltage. So in this case, in a battery, it's the difference between the voltage here and there, which, well, let's call that 0 for the moment. So the current is going to flow from higher voltage to lower voltage. So that's how we get our circuit. So now we have voltage pushing our water through the pipe, pushing our holes or current through the wire. And then how much flows through? If you got your pipe, you can measure how much water is flowing through it, right? How quickly it fills up the bucket. Well, we have something similar here. We call that current. Sometimes, let me show you all the symbols. I'm not sure which ones Rich uses. Okay, he uses E. E stands for electromotive force, which is equivalent to voltage. And you'll see both of them. Then there's I, is the amount of flow. Stands for current. So let's say E is electromotive force, which is the same